Great.
Okay, so good afternoon. Sorry, we are a few minutes late, but we had to swap laptop at the last second for very complicated technical reasons. Okay, I think this is the first webinar of the new year. Yeah, so we are very happy to have old friends, yeah, from old Durban times. Yeah, Ryan Sweke with us. Ryan did his PhD, what was it, 2018, 2017?
2016.
2016, okay. Back in Durban. Then he spent 4 or 5 years in Berlin as a postdoc with Jens Eisert.
Yeah.
And a couple of years in the US with IBM in, no, not Santa Barbara.
In San Jose.
In San Jose, sorry, San something. Yeah, San something in California. And now since a month or a few weeks, he's back in Cape Town at Ames, where his official title is something like German Research Chair or something like that. Yeah. Okay, so we are very happy that Ryan is again close by. Yeah. And Ryan, we're looking forward to interact many more times, in particular because this year is a year of quantum science. So we need to do lots of things. Yeah?
Yeah.
But Ryan, please, you're welcome too. And if you speak close to the laptop, people will hear you. Great. Let's see.
Yeah, thanks, Francesco. Like Francesco said, I did my PhD with him many years ago now. And since then, I've spent a long time in different places. And after many, many years, I'm now officially back at Ames. And yeah, very excited to be there and to be here in South Africa. And this talk is kind of a part of what I think of as a tour of advertising the fact that I'm here. I'm super excited to collaborate. I have lots of like space and time and energy and motivation. And the idea of this talk is to give you an overview of the many different types of things that I'm interested in. Like you will find no details in this talk. Like there's no kind of proof sketches or anything like that. This is kind of like a high level motivation for like why I decided to ask and answer the sort of questions I did in the last 5 or 6 years. Like, so if anyone has any questions about technical details, put up your hand, we talk about it either now or later, or in my office at Ames next week. Like anything is possible. And yeah, feel free to interrupt me at any time. Okay, yeah.
You change your title. PQCs.
Yeah, okay, so good point. This talk has a different title to the one that got advertised. The content is the same, but maybe this is a more balanced title. I took this from another slide without noticing that changed, but it's the same. You'll get what was advertised, I promise. Okay, so to be honest, I had no idea really how big or how small the audience would be for this and what background everyone has. So the first slide, which you can't see the titles of any of the slides, that's not ideal. Yeah, there we go. Okay, the first slide is what is a quantum computer? And I guess many of you here know what a quantum computer is, but like, I guess when I did my PhD with Francesco 10 years ago, I was more or less a physicist. And over time, I have drifted very much into what I now think of as being a theoretical computer scientist. And I'll give you my like TCS, theoretical computer science definition of a quantum computer, which is maybe interesting for you, even if you know it. So what is a quantum computer? A quantum computer is any device or any kind of mathematical object that satisfies 4 properties. The first property is that it should have a collection of stable qubits. And as you know, like from a mathematical perspective, a qubit is nothing but a unit vector in the 2-dimensional complex plane. Bits would be just like the unit vectors on the x and the y axis, and the state of a qubit is fully specified by a unit vector in the complex plane. So the first thing that a quantum computer is it's a collection of qubits. So it's a vector that lives in the Hilbert space, which is the tensor product of these 2-dimensional spaces. Now, like a computer is only interesting if you're able to prepare the input state to whatever problem you're trying to solve. If you want to factorize a number and you can't program your computer to represent the number you're trying to factorize, you're not going to get anywhere. So a quantum computer has to, in addition, have the ability to prepare a fixed initial state. And in general, like it's always totally sufficient to just start from the state 0, 0, 0, the all zero state. Okay, the third thing, and of course this initial state is just part of this like due to the n-dimensional Hilbert space, which you get by taking the tensor product of the Hilbert spaces. Okay, and now like we can prepare a state and we have to be able to compute. And because states in quantum mechanics are unit vectors, whatever a computation is, it should preserve the norm of the state. And well, unitary matrices are precisely those operations. So in a quantum computer, the computation is represented by a unitary, and we should be able to implement arbitrary unitary operations if we're going to say we have a quantum computer. So that's the third element. And then finally, the fourth element is that we should be able to extract the solution to the computation. At the moment, at the output of this diagram is a quantum state, but like that doesn't tell us the factors of a number. So we should be able to make qubit-specific measurements. Okay, and now, of course, like the ability to implement an arbitrary unitary operation seems essentially impossible. This is like a continuous manifold. There's like infinitely many of them. But luckily, we know that it's totally sufficient to implement some small, discrete, finite universal gate sets, all single qubit gates and CMOS. And with this, we can implement any unitary operation up to any accuracy that we want to. So yeah, we replace our unitary with some circuit of gates that when you contract them, approximates the unitary that implements the computation you want. And the computation is now defined by the unitary. And of course, like you probably know, when you measure, what happens is you get a sample from a probability distribution. So if you measure in the computational basis, you're going to get some bit string, some like each of these xi's is a bit, and well, you'll get bit string x with this probability here. This is the Born. This is the Born group. And if the computation is defined by the unitary, you should design the computation in such a way that when you measure, the probability distribution of a bit strings is concentrated over whatever is the correct solution to your problem. So it should have the property that when you measure the output state of this computation many times, you're most likely to, or like you can extract the answer to your problem from this probability distribution. Okay, so this is kind of like a mathematician's perspective on what a quantum computer is, or like with these four things, you're kind of like ready to go. And these are not original to me. These are the DiVincenzo criteria, which I think he formulated them in 98 or 99 or something like that. Okay, so that's a quantum computer from my perspective. I'm lucky enough to not have to think about trapped ions or superconducting qubits or Josephson junctions, or like, for me, this is a quantum computer. Okay, so why a quantum computer is interesting. Like some people just like defining computational models, but other people have like a higher bar for why something is interesting. And in order to like answer this question, we first have to kind of understand what makes any computation interesting. And basically, like a computation is interesting if it's efficient, but we need to formalize this notion of efficient. Like until we can formalize the notion of what efficient means, we can't say that something is either efficient or not. And so for a quantum computer, there's this notion of the circuit depth with the number of layers of gates that you have to implement the computation that you're interested in. And basically we say that if the circuit depth is a polynomial function of like whatever represents the problem size, then this computation is efficient. And this is a very good common sense definition, because imagine that you had a circuit depth whose length scaled exponentially with the problem size. Let's say the problem size is the number of bits that you need to specify the number that you want to factorize. Even if you could do it for 10-bit numbers, if it scaled exponentially, you would die at 11-bit numbers. Like, or if you could do 11, you would be completely dead at 12. But like when something scales polynomially, we know that kind of if you can do it for one like size instance, you can probably keep doing it for like much bigger size instances, because the length of the circuits is going to grow slowly. Like a polynomial is code for slow enough. Of course, you can have faster than polynomial, you can have logarithmic or constant, and this is like really gold. But we're happy if it's polynomial, and this is what we consider to be an efficient algorithm. Polynomials are also great because they compose. If you plug one polynomial into another, you're left with another polynomial. So when algorithms have a polynomial efficiency, you can use them as subroutines in other efficient algorithms without worrying about anything blowing up. Okay, it just means that the time to implement it scales reasonably with the problem size. Okay, and now like once you have a notion of like what is efficient or not, you can start to separate any problem that you can think of into sets. And like you can say that there's a set that contains all problems that we know efficient algorithms for. And the name of that set is P. problems that you can solve in polynomial time. The P stands for polynomial with a classical computer. And so problems in P are the sort of problems that we solve all the time, like solving linear systems, for example. That's a problem in P that we know how to solve. Okay, and then there's this other class of problems, NP, and this is the class of problems that we actually don't know how to solve them at the moment. We don't have good algorithms. But if you give me a solution, I can very quickly check that that solution is correct. And the paradigmatic example of this is the problem of factorizing a number. If I give you a gigantic number and I promise you that I multiplied together two prime numbers to get this big number, and I ask you to give me the factors, like, you're going to struggle. You can try your best, but you'll struggle. But if you tell me, like, oh, this is the solution, these are the two primes, it's easy to check that you're correct. I multiply them together and I check that I get the original number. So these are problems that have like efficient certificates of being correct. Okay, and then there's NP complete problems, and these are kind of the problems in NP, which are like the hardest problems. If you can solve one problem in NP, you can solve all of them. And yeah, that's a class that's very well characterized. And now the cool thing is that as soon as you now we have a different model, quantum computers. So we can draw another set, which is BQP, which is the set of all problems which could be solved by quantum computers in polynomial time. And like for quantum computers to be interesting, this set better be bigger than this set. Like if this set is inside this set, there's like no point to it. Like quantum computers are done. Like we can like give up already. So basically, like the very first thing you should ask with like a TCS hat on is like, is this set bigger than this set? And luckily, like we think that the set is bigger than the set because of the fact that we know a quantum algorithm for factorizing numbers. And at the moment, we don't know any polynomial time algorithm for factoring numbers. But one could come tomorrow, and then we'd be back to like not knowing whether quantum computers are worth anything. Okay, so we know that there exist problems which we can solve efficiently with a quantum computer, but we don't yet know if we can solve them efficiently with classical computers. And like this gives us motivation to like try build these things and to study them more. And of course, the big question is like, are there more problems? And like it's very important that we like strongly don't believe that there are any NP complete problems that are in BQP. We have lots of different types of evidence that quantum computers can't solve NP complete problems. But the real question for someone working in quantum algorithms is like this what was called like NP incomplete region. Like, are there other problems in here which we can put into BQP? This is like the job of someone who does quantum algorithms research. Okay, and like I should also say that even if you don't care about like applications at all, you learn a lot of fundamental things about the world by thinking about quantum computers. Like, what are the limits of computation, of like storage of information? I mean, like people are learning about like the dynamics of black holes by like thinking about the way that quantum computers store and process information.
Okay. So you feel that the boundaries of BQP is even beyond NP?
So we do think that there are problems that are harder than NP. That
what do you call it?
I mean, so that like these classes are just like the first two classes in like a whole hierarchy that's called the polynomial hierarchy. The way you define the polynomial hierarchy is you say like, okay, now let's consider like an algorithm that's polynomial, but it has access to this like magic box that can immediately tell it the answer to any NP complete problem. Like that's called giving it an NP article. And if you do that, you define like the first level of the polynomial hierarchy. And then you can take that algorithm and you can say, what happens if we give that algorithm another magic box that can answer even hard problems? And so basically outside here, you just have the whole like landscape of classes. And if you're interested in this, there's an amazing website called the Computational Complexity Zoo, which like gives rigorous definitions and examples of every complexity class under the sun, of which there are probably by now 1,000. Like, so this is like a very, very, very rich landscape. For instance, like you could say, okay, what happens if we impose space constraints? So far, this is only like the only constraint is time. Like something goes in here if we can solve it with polynomial time. But what happens if we only have like a constant number of bits available to us? Then you get some other class that you could ask what's in here. What happens like, so there's a rich landscape of complexity classes. And I mean, this is the substance of what complexity theorists do. And this is the kind of like most basic picture you need in order to understand like why quantum computers are interesting. A good point is that like this is a guess. Like we don't know that this is true. Like if you like, we don't know whether NP is any bigger than P. And if you solve this, like I promise you, you'll be the most famous mathematician on planet Earth tomorrow. Like, Okay, so quantum computers sound great. Like, where are they? And this is, I guess, the stuff that you all know, that in the 80s, quantum computers were really just like drawings on paper. And now they are like real devices. That's at Yorktown Heights at IBM. Somebody configuring things. And they have more or less 100 qubits now. And like everyone under the sun is putting in as much money as they can into quantum computing to like get these things bigger, to get more people using them, and to figure out what they can do. And yeah, like the important thing is that you can really use these. Yeah, like this is sitting at IBM, but as I'm sure you know, like you can create an account and you can go and you can run circuits on these devices. Okay, so now the natural question you should have is like, are your credit card details safe? Because like some of you may or may not know that like most of modern public key encryption is built on the fact that we don't know if there's an efficient algorithm to factorize numbers. This is like how the RSA crypto system is built. And so if you could factorize numbers, which we claim we can do with quantum computers, like we can break a lot of modern cryptography, at least modern cryptography of the last 45 or 50 years. And so that's a real question, like, are your credit card details safe? Or like, are your end-to-end encrypted WhatsApp messages safe? Like all of this can be broken with quantum computers. And the reason that it's safe, at least for the moment, is that like noise is a major obstacle in building quantum computers. And I guess in this group, like everybody knows the like open quantum systems picture of quantum mechanics and understands what noise is. But like essentially what happens is when you try run a circuit like this on a real device, like both when the gates are idling and when the gates are being executed, all sorts of different things that you don't want to happen. There's dissipation, there's decoherence, cosmic rays happen, the device is not perfectly calibrated and you don't rotate the qubit the exact right amount. All sorts of like imperfections and instabilities affect the computation. And what you get out at the end is more or less garbage at the moment for like most of our quantum computers. And so basically you're sad and you need to figure something out. And luckily, like over the years, people have developed this field of fault-tolerant quantum computing, which is precisely aimed at understanding how to do quantum computations in a way that's tolerant of faults and errors. And at a very high level, the idea is that imagine you want to run a circuit on 4 qubits, but you know this qubit is messy. And so you basically say, let's give some additional qubits to each qubit to kind of like help it resist the effects of noise, to like make the information more redundant. So the first thing you do is you kind of make your system redundant. And then you have to figure out like what the correct gate is, like what the analog of the actual gate you wanted to do is on this like redundant system. And then you do that gate, and then some noise happens. And then what you have to do is you have to do some kind of measurements. You have to give those measurements to a classical computer. And then you figure out from those measurements what like additional operations you should do on your device to like correct the errors that occurred. And then you just go through your circuit doing this. And at the end, if you did everything right, you hopefully get the answer you wanted. And so like a fault-tolerant quantum computing scheme or quantum error correction scheme has many different components to it. You have to figure out like how to make the qubits redundant. This is called how to make logical qubits out of physical qubits. You have to figure out like what gates you should implement to do the analog of like the original gate you want. You have to figure out what operations to measure to like diagnose what went wrong in between. And then you have to figure out like how to correct it again. And if you do all of these things, you come up with a quantum error correction scheme. And this is an extremely, extremely active field. I think maybe quantum error correction is the most active subfield of quantum computing at the moment, at least in my perception or my perspective. But that's in the future. For now, we have like what people have called noisy intermediate scale quantum computing. And noisy intermediate scale quantum computing, you just say like, this is what I've got. It's noisy, it's small, but it's limited depth. But let me just see what I can do with it. Like I have it and let me see what I can do. Okay, so that's the whole setting. And now that we live in a world where machine learning is changing like absolutely everything that is going on. And so like if you look at this and you say, well, what should you do with quantum computers? Like you might be tempted to say, let's do machine learning. And for the rest of this talk, I'm gonna give you, or maybe for the next like third of the talk, I'm going to give you some perspectives on my take on like one approach to doing machine learning with quantum computers. And the approach that I'm going to talk about is so-called variational quantum machine learning. So let me start off by kind of telling you what variational quantum machine learning is at a very high level. So the idea is in like lots of modern machine learning, the idea simply is that you want to learn an object, let's say a function or a distribution, and you don't know what it is. So you try to parameterize like a whole class of functions or a whole class of distributions using neural networks. Like you just define a neural network that has the right structure. It generates samples from a distribution or it labels objects, but it should have parameters that you can optimize and that hopefully in the end you arrive at the right function. And the idea of parameterized quantum circuits, of variational quantum machine learning is just to parameterize quantum circuits, to use quantum circuits as like a variational manifold or as a model class. So imagine you want some function which maps from R3 to 0, 1. So it classifies like elements in three-dimensional space into like the unit interval. So what you could do is now you could take a quantum circuit, a quantum computer, and you could make some of your gates like depend on the input to the problem. So this Rx or Z or Y, these are like gates that rotate your unit vector like in certain directions or on the complex plane, and you just make these depend on like the input to the function. Okay, so the blue ones are input gates. And then you can have other gates which depend on parameters that you're going to optimize. So these kind of grayish pink gates are variational gates. And then you can put in gates to generate entanglement and all the rest of it. And what you end up with is you end up with a unitary that's parameterized by both the input to the problem X and some variational parameters, theta. And then what you do is you measure some observable. Like here, what's shown is the expectation value of the Z observable on the first qubit. And we know that this is going to be some number like in the range that we want. And ultimately, you see this rule is the rule for how we define a function from our parameterized quantum circuit. We say that the value of the function is the expectation value of the measurement of the Z operator. Okay, and like so there's the class of all functions that are possible. And what we do here is we define implicitly some subset of those functions. So like if you sweep over all possible parameters here, all theta 1, theta 2, theta 3, like this will allow you to realize some subset of functions. And those are the PQC functions, the functions that correspond to parameterized quantum circuits. And I could also draw on there all the functions that you can realize with a depth 2 neural network of 40 neurons in the first layer and 30 neurons in the second layer. Like all of machine learning works by defining some subset, parameterized subset of objects and optimizing over that subset. And variational quantum machine learning, as it has developed so far, optimizes over the subset of functions defined by a parameterized quantum circuit. Okay, and now you can do the same thing for distributions. In fact, for distributions, it's much easier. So let's say we want a probability distribution over length 4-bit strings. So this is a probability distribution over 4 bits. What we can do is, again, we can define a circuit and we can make some of the gates depend on variational parameters. And now, like we know when we measure this, so now we get a unitary that depends on theta. And when we measure this, we know that we're going to sample from the distribution with this definition, the Born distribution. And so again, we have the setting that you can consider the like space of all distributions, and we know the thing we're trying to learn lives somewhere in there. And we define as our model class the subset of distributions that we can realize by measuring the output states of parameterized quantum circuits. So this is really, from my perspective, the bird's eye view of variational quantum machine learning. Find a way to define a parameterized set of the type of objects that you're interested in. Functions, distributions, whatever you want. There's more options than this. Okay, and then what you do, of course, is then you just do standard machine learning. Like in standard machine learning, you make a guess for the parameter that you want of your neural network. Then you check how good it is. You send that result to a classical computer. The classical computer runs some optimization algorithm. So you send it to the classical computer runs some optimization algorithm, and it tells you how you should update the parameters. And what goes on in here can be like gradient descent, it can be like non-gradient based methods, it can be anything you want. So sometimes people also call this like hybrid quantum classical machine learning, because like you're using the quantum computer to evaluate the function of the distribution and the classical computer to do the optimization. But I think that variational quantum machine learning is a term that I like more. Okay, so now like imagine we're doing quantum machine learning with variational quantum circuits. Like, what do we want? Like, if you could choose, like, I think about this sometimes, like, imagine there was a magic box and I push it and then it just spits out a theorem with a proof. Like, what theorem would I like to come out of that box? Like, in terms of motivating quantum machine learning? Well, like, ideally, the most ideal thing we could want would be rigorous guarantees for state-of-the-art learning frameworks on real-world data sets. I mean, the best thing imaginable would be if you could tell me that if you run this algorithm for 347 steps on ImageNet, I guarantee you it will get you 99.9% accuracy. Like, I mean, this would be like a gold standard theorem. And so what you want are kind of rigorous guarantees on like the amount of data the algorithm will use, the amount of time it will run for, or the generalization capacity, like its ability to do well on examples that it hasn't seen yet. And I mean, you would like these guarantees for things like neural networks or parameterized quantum circuits, so like what people think of as being state of the art. And ideally, you would want it for real world data sets like natural language, protein shapes, etc. And even better, like now, like the dream of like a quantum machine learning person would be if you could have what are called like quantum classical separations. So a quantum classical separation would be a theorem that says, for some problem, if you want to solve it using any classical machine learning algorithm, the amount of data that you need has to be bigger than some threshold. Like if you don't have that much data, you just like, it will not work. Like you will not be able to get a meaningful solution. So what you want is a classical lower bound. You want to prove that no classical algorithm can do well unless it has a certain amount of data. And then simultaneously, you would want to prove a quantum upper bound. So you would want to prove that any classical algorithm needs at least this much data, but then you would like to prove that there's a specific quantum algorithm that needs at most this much data, where this number is less than that. Because then you've really proven that the resources needed to solve this problem are meaningfully different for quantum computers and classical computers. Quantum computers can definitely do it in a regime where classical computers can definitely not do it. Like this is the name of the game in kind of like the mathematical foundations of quantum machine learning, proving theorems of this type for specific problems. And it's tough because here the problem is like creativity in the sense that you have to prove that no classical algorithm ever will be able to do it without this much data. But you have to kind of counter, like you have to defend against any possible algorithm someone could come up with in the future. Like lower bounds are notoriously hard in computer science. And here there's also the problem of creativity in the sense that like you have to come up with a good quantum algorithm. Like there's no part of this which is easy. Okay, and you could also prove similar like quantum classical separations for accuracy. You could say like let's fix the amount of data and then prove that no classical algorithm can get like better than this accuracy. But here is a concrete quantum algorithm that can get better accuracy. So you could have separations for data, you could have separations for accuracy, for time, for generalization, all sorts of stuff. Okay, but like I said, this is hard. Like people don't prove these sorts of theorems, even in classical machine learning. Like you just don't see them for real state-of-the-art neural networks and data sets. So like we know what we want. We also know that we can't get it without winning Fields medals along the way. And so like, how can we get what we want? So like the first thing you should always do is simplify the problem. Like this is kind of problem solving 101. Like we want these amazing theorems that apply to state-of-the-art models and real data sets, but we don't know how to do it. So let's simplify the problem. Instead of considering some like data set like ImageNet or stock market or protein configurations, and instead of considering like real state-of-the-art models, why don't we first say like, let's just consider a toy data set. Like, so we take away ImageNet, we take away like natural language, and we just imagine data which we like understand. So data that has a concise mathematical description, and that could maybe encode a hard classical problem. So for instance, like discrete log data, I mean, imagine you just take a function, which is the discrete logarithm, and then that's the function you're trying to learn. Like we have a mathematical description of that function. And in addition, because we're trying to like design problems that are hard for classical computers or machine learning problems to solve, we can start from problems that we think are hard for these devices to solve. Okay, and I mean, we've cheated here, but like, we're just trying to like get our foot in the game or like get our foot in the door. And then the second thing you can do is instead of considering like a parameterized quantum circuit updated by stochastic gradient descent, which is extremely hard to analyze, you could say, let's just imagine what we want is to construct a fine-tuned quantum learner. So this quantum learning algorithm doesn't have to succeed on any problem except this one specific problem. Like, and so importantly, like for now, we say like, ultimately we want to prove theorems about stochastic gradient descent and parameterized quantum circuits. But before we do that, like we can't hope that a generic algorithm can do well if we can't build a very specific algorithm to do well. So it's kind of like a first step. Like let's look at fine-tuned quantum learning algorithms for fine-tuned problems. So really like we're going to try to construct a quantum learning algorithm that's like tailored to exploit the known mathematical structure of the data set. Okay, and like also ideally we would like these things to work on NISQ devices, but like also we're happy if in the beginning we can just say it works on a fault-tolerant quantum computer. Okay, and now it's important that a separation here, like if I manage to prove a quantum classical separation with these assumptions, it really provides no evidence at all for using generic quantum learning algorithms for real-world problems. Like I haven't made any statement about like PQCs and about real-world problems. But my perspective is that this is really a necessary condition for the like more general setting, in the sense that if you can't prove a quantum advantage for fine-tuned quantum learning algorithms on fine-tuned problems, you can kind of forget about proving it for like PQCs on ImageNet. Like this is like the mathematical like first step in the right direction. And if you can't do this, like I think like you should stop until you can. Okay, so the good news is that we can do this. We can do it for generative modeling and we can do it for density modeling. So these are two types of probabilistic modeling. And like I promised you, like in this talk, I'm just going to motivate the questions that I've thought about in the last few years and not tell you like the answers. But in these two papers, you can find the details of precisely how we constructed very specific generative modeling problems and very specific like quantum algorithms that solve those generative modeling problems, which have the property that we can also prove lower bounds for them against classical algorithms. So we construct problems that we prove no classical algorithm can solve meaningfully, but for which we give like an explicit quantum algorithm that does it. Okay, and like remember that I'm the first one to say that like you should not take this result and then go say that quantum machine learning is going to work. And funny enough, there are companies that took this result and said precisely that this is evidence that quantum machine learning is going to work in press releases. And like we had to write to them and say like, no, it's wrong. It's not the case. And in case you're wondering like how to do this, like you do it with a lot of cryptography, because cryptography is the field that aims to construct like protocols which are hard for like eavesdropping for attackers to break. And so if you want to design machine learning problems that are provably hard for classical algorithms to succeed on, you should look to cryptography for inspiration how to do this, because they've been doing this for 40, 50 years. So really like underneath all of this are the tools and methods of the foundations of cryptography. And like lately, more and more, like what I'm working on is kind of questions at the intersection of cryptography and machine learning. And that's another way to like view this. Okay, so we passed the first hurdle in the sense that we know at least that if we bias everything in favor of quantum algorithms, the problem, the learning algorithm, then it's like they pass, like you can do it. Like quantum learning algorithms can pass. But now, of course, like the next step is like once you've solved the first homework problem, you got to go solve the second one. And now like, what is the second homework problem? You've got to relax some of the fine tuning. And so originally, remember, we had like this fine-tuned quantum learning algorithm and the fine-tuned data set. But let's say now, like, okay, we want to prove something about parameterized quantum circuits. Like people at IBM, people all over the world, they're doing experiments with these things all the time. This is what people care about. Let's prove a theorem about parameterized quantum circuits. Okay, so now like you can ask yourself, what data set should I consider? And you can say like, I want to remember what the name of the game is. I want to confine the problem that's easy for the quantum learning algorithm and very hard for the classical learning algorithm. And so you can ask yourself, like, what problem do I expect parameterized quantum circuits to be the best at? And the answer to that problem is that the data set that you should use is precisely learning the model class of parameterized quantum circuits. I mean, remember in the beginning, we said that parameterized quantum circuits, they define like some subset of functions. And those functions are precisely the functions you would expect would be easy to learn for quantum computers. Like we know that the function was generated by a quantum computer, a parameterized quantum circuit. And so if you want to kind of find like the best candidate for a problem that would be easy for a parameterized quantum circuit, it's learning the like a parameterized quantum circuit. So remember, like in the generative modeling case, for instance, like we consider all distributions now that are the outputs of some like quantum circuit with some fixed structure. We could say like all quantum circuits that have a constant depth and like whatever gates. Okay, and the cool thing about this data set is that even though it seems like quite artificial, it's not natural images, it's still very generic. In fact, we know that if you want to sample from these distributions, you can't do this with a classical computer. These are all the quantum supremacy experiments. The quantum supremacy experiments precisely say that sampling from the output distribution of a quantum computer is hard for classical computers. And so here we kind of want to prove that it's like we want to understand how easy or difficult it is for a quantum computer to learn them. And we would also like to prove that they're hard for a classical computer. Okay. And also because it's hard to rule out like every single classical algorithm that ever has been and ever will be, we can also like find a way of defining some smaller class of algorithms, which we can call like practical algorithms people use every day, let's say. And now like we're in the setting where we have like a very well-defined mathematical problem. The problem is like prove that quantum computers, that parameterized quantum circuits can learn these distributions, prove that classical linear algorithms cannot. And if you manage to do this, you actually would have provided some good evidence in favor of these variational quantum machine learning algorithms. You would have shown that there's some like non-trivial task that's like almost the real world, and that they're much better at than classical devices at. And of course, if there's no separation here, so if you prove that like this problem of learning these distributions is like hard for quantum computers even, then you've provided some evidence against using PQCs. Basically, what you've said is there's this problem, which is the problem you most expect quantum computers to be good at. And like if you prove that it's hard for even quantum computers, then it's kind of like, maybe they're not going to be as good as you think they are. And interestingly enough, we can prove that the problem of learning this PQC model outputs is hard actually for quantum computers as well. So like kind of what you would want, the opposite happened. Instead of proving that quantum computers can do this and classical computers can't, we proved that this problem was hard even for quantum computers. Like we managed to prove a lower bound for quantum computers. Quantum computers need at least super polynomial number of samples in order to learn these distributions. And then in fact, we went further and we actually proved that these problems are extremely hard. And the way that you do this is like, to say that a problem is hard, what you need to do is prove that there's at least one quantum circuit that you can't learn the distribution of. And that's what we did here. And in this paper, what we proved is that like an overwhelming fraction of them, 99.9999% of all the distributions are hard to learn from quantum computers. So this is like a worst case hardness result, and this is an average case hardness result. So the situation is basically as bad as it could be. Like quantum computers are terrible at learning their own output distributions. And like, if they can't do that, maybe like they're not going to be so good at learning distributions in the real world. So in my perspective, like this is good evidence that you're unlikely to get a quantum advantage from these models. Okay, great. So far, all I've spoken about has been about unsupervised learning, about learning probability distributions. You're given a sample from a probability distribution, or you're given multiple samples, and you want to learn how to describe the distribution or how to generate new samples. So now, what about supervised learning? Supervised learning is something where there's some function, it labels dogs and cats, and you want to learn how to label images that you don't know the answer for. So remember that PQC functions are a subset of all functions, okay? And now, like similarly to the case of distribution learning, we would just like to start getting like a mathematical handle on these objects. Like, what are these functions? Because if we can kind of understand these functions, maybe we can start to understand like whether they're a good idea to use them for machine learning or not. And so there's a good question here, which is like, which subset is this? For example, imagine this was the subset of linear functions. Then you would know immediately, like, this is ridiculous. Like data in the world, it's not linear. Like if these are linear functions, we can forget about it already. Like, as a sanity check, it would be nice to kind of just know that there are like interesting non-trivial functions in this class. So the first thing we can do is we can prove that these functions are actually trigonometric polynomials. So these are things like sine to the power of p, like plus cos to the power of q. And we can prove that these are trigonometric polynomials where like the frequencies that appear are like constrained in specific ways. And this is actually a paper with another one of Francesco's ex-students, Maria. And so we managed to do this a few years ago. And the nice thing is it unlocked a whole lot of new results that we could do almost immediately. Because now, like parameterized quantum circuit functions, they're like very hard to work with. They're not explicitly defined. They're implicitly defined. You draw the circuit and like that's the definition of a function. Like it's very hard to prove anything about that object. But as soon as you know that they're trigonometric polynomials, well, you can immediately do things like prove generalization bounds. So a generalization bound is a statement that says that if I get this accuracy on a test set, then I can be guaranteed that I will get at least this other accuracy on future data that wasn't used in testing, in training. And this is like really important because imagine you train a model and it gets 100% on everything you trained it on. Like if you have no guarantee that it will do well on other data, it's basically useless. And so like really before you can start to like consider using any quantum or machine learning algorithm, you should know it has this property. But now, because we know that PQC functions are trigonometric polynomials, we can use all the tools of generalization bounds to prove things for trigonometric polynomials that also hold for parameterized quantum circuits. So that's the first piece of good news. But then there's some bad news, because it also allows you to do something which is develop what people call classical dequantization methods. And what I want to do in the next slide is tell you exactly what I mean by like a dequantization method and how this insight about parameterized quantum circuits for supervised learning helps you develop them. So basically, imagine what's happening. So this is the situation. You have a set of all functions, like the one you're trying to learn could be anywhere in there. You have the set of PQC functions, and you know that there's they're a subset of trigonometric polynomials. And now imagine someone's like, I'm going to use my my variational quantum algorithm. And you want to prove to them that it's a bad idea. Like, it's just a bad idea to use a variational quantum algorithm. How would you do this? Well, you would ask yourself, is there a classical algorithm which is provably just as good as the PQC algorithm? So it has the property that I can prove to you that it will be just as good as the parameterized quantum circuit optimization. And I can also guarantee to you that it will run efficiently. If you can answer yes to these two questions, then you've basically proven that it's silly to use the quantum algorithm. Because like there's a classical algorithm which is provably just as good and runs efficiently. And so like one way that you can construct an algorithm like that is to say, well, let me take inspiration from the way the quantum algorithm works and see if I can just do those things on a classical computer somehow. And once you know this property of PQC functions, that they're a subset of trigonometric polynomials, it's actually pretty easy to think how to come up with a good classical algorithm that like should be better than the quantum algorithm. What you do is you just say, instead of optimizing over the PQC functions, why don't I just optimize over trigonometric polynomials? You know, it's like saying, if you have a depth 2 neural network, all of those functions can be realized by depth 3 neural networks. And so like, if you want to beat depth 2 neural networks, just go to depth 3. Like that's kind of what we're saying here. We're saying, okay, like you could use your quantum circuit, but if you just go optimize over trigonometric polynomials with the right structure, like you're exploring a broader class of space. But unfortunately, there's two problems with this approach. The first problem is that the trigonometric polynomials can be exponentially hard to evaluate. It turns out they can have like exponentially many terms in them, just like you could have a polynomial like x cubed plus y to the power of 5 plus z to the power of 7, and this could go on forever. And it turns out that the trigonometric polynomials that are generated by parameterized quantum circuits, like they can be exponentially long, which you can't do efficiently on a classical computer. The second problem is that the output function might generalize worse than PQC optimization. So counterintuitively, like you might think that the best thing you could do would be to just use the set of all functions as a model. But the problem is, like, if you have a set of all functions, then you could learn the function that exactly works for every single element in your training set. But that function will probably do very badly on data it hasn't seen anymore. It's overfitted to the training set. And so basically, the bigger you make the space of functions that you optimize over, the more likely you are to overfit and do worse on data that you haven't seen. And so now, because we're optimizing over a bigger class of functions, there's the risk that we overfit. And so if you want to like answer this question at the top, you have to do two things. The first thing that you have to address is this exponentially hard to evaluate. And luckily, there's a solution to that. And the solution is like a standard solution that people use in theoretical computer science when they want to make something run faster, which is just use a random approximation. So instead of using the whole trigonometric polynomial, just randomly select like some polynomial number of terms. And if you do this enough times, each time selecting a different random subset, it turns out you can get good approximations of this exponentially sized object. So the first thing you should do is randomize. And the second thing that you should do is you want to prove that the classical algorithm should generalize well. So you should prove a generalization bound. Like you should come up with some proof that even though this set of trigonometric polynomials is bigger, it's not so big that it will generalize badly. You should prove a generalization bound. And we do both of those things in this paper, potential limitations of random Fourier features for dequantizing quantum machine learning. You can find it there. And unfortunately, the answer to this question of whether there's like classical algorithms, which are, I mean, it depends, unfortunately or fortunately, depending on I mean, I should say that like for the last few years, I've occupied the position of like skeptic of quantum machine learning. So for me, like a good result is when you prove that a quantum machine learning algorithm can't do something. Like at least that's the perspective I've been taking for the last 5 years. Because I would like to put this on solid foundations. Like I feel like it's better for the field as a whole if we really understand the limitations of these things. And so the answer, unfortunately for me, is that sometimes the PQC algorithm the classical algorithm is as good as the PQC. And sometimes we can't say it. Basically, our generalization bounds are not tight enough, and the like approximations we have here are also not well controlled enough, so that like sometimes it works and sometimes it doesn't. Okay, so that's about dequantization. So far we've seen that good evidence that quantum computers, like you probably shouldn't use them for generative modeling. And now we've seen that like sometimes there are classical algorithms which are just as good as quantum algorithms for supervised learning, but there's some room to move here for those people that are still optimists. But you have to be aware that you're not in the regime where they can be dequantized. Yeah.
Just a quick question on that. So when you make sure I understand, or you refer to like this subset, when you talk about a PQC in this case, it's like one with a fixed structure. And then you have basically what kind of trigonometric polynomial expressivity or like the reach of that trigonometric polynomial, and then you test whether there's a classical thing
that uses
that better.
Exactly.
Okay.
Yeah.
So like you had a different structure.
Yeah,
you could like if you chose a circuit that has a very limited thing, so like okay, well, like with this thing, I'm always going to be better classically.
Exactly. So like
what's the expressive circuit anyway?
I think that's like the real contribution of this paper. Okay. The real contribution of this paper is ruling out the structures that like you can do just as well classically. But like you kind of have to start like formulating things in terms of like circuit depths and structures, and like these theorems, they like help you do that. Yeah, you're totally right. Okay, so finally, I'm going to talk about in the last 7 minutes, like something that is my like absolute favorite topic of the moment. And it's like, even if it works, can we trust it? So like, imagine this situation, which you don't have to work too hard to imagine because it's the real situation, which is that you have Alice and you have Bob, as always. And Alice has a classical computer. Like we are all Alice. We have MacBooks, okay? And Bob is at IBM. Bob was me like a year ago. And like, I'm claiming to you that I have a quantum computer. Like you've seen pictures of it on the internet, like you've logged in and you've like run jobs on it. But like, what happens to you if I'm just lying? Like I could just be lying, because what's happening at the moment is that Alice is paying Bob, like we are paying IBM, and IBM is like doing something, and then they're sending us a solution. And they're like, like But we're only using the quantum computer for problems that we like can't solve ourselves. So like if we can't solve it, like how do we know that they're not just like guessing? Like how can Alice trust Bob? Like the real problem is like she can't solve the problem herself. So like now we don't necessarily have that problem because like we can check things, they're small enough. And there's some problems that have like very easy certificates, like factoring, like it's easy to check answers right. But think about machine learning. Like in machine learning, like you have no idea like whether like some function is the best one that they could have found. Like IBM could really be like sucking their thumb, sending you some function. It does slightly better than the one you did, but it's just because they used the GPU. Like they never actually used their quantum computer. Like this really, really could happen. And so like Alice, what she really needs is a verification method. Like she needs like something she can do that guarantees her that Bob did what she paid him for. And so like in the language of computer science, these are called interactive proofs. Like you have to develop a protocol, like which is a sequence of questions Alice can ask Bob, and then Bob has to answer them. And like these questions should be designed in such a way that like Alice can use them to check whether Bob is trying to cheat her. Again, like basically the rough idea here is that you use randomization. Like what Alice does is she like sends Bob like a whole bunch of different questions, some of which she knows the answers to, and some of which she doesn't know the answers to. And like she randomizes them so that Bob doesn't know which ones they are. Like this is the very high level idea. Use randomization and like hidden knowledge. But like I really believe that until you have these verification methods, like this is like quantum computing is not even off the ground, like until you can do this. And like we are not the first people to think about this. Like solving this problem for like general quantum computations, like it is the subject of what's called verified blind quantum computing. And this was basically solved in 2009 by like Sheffy and Fitzsimmons. And like it was really improved like in 2019 by a very, very, very good researcher, Mila Mahadev. But like the thing that's new here is like for learning, because in learning there's this whole like other problem, which is that if I want you to do a computation for me, it's kind of like I know exactly what I want you to do. But imagine I want you to run a learning algorithm. Like how can I check that you even use the right data? Like the data is the thing that makes this super hard. And well, it turns out that we can actually develop really rigorous interactive proof protocols for the verification of quantum machine learning for toy problems. Like the problem that we consider is the agnostic learning of like Fourier sparse functions, but like it's a start. And personally, I'm very proud of that paper because it's the first paper I wrote that made it into like a real theoretical computer science conference, and like it's a personal milestone that I'm very happy about. Okay. But interestingly enough, this is actually just one example of a much more general problem. So, and the more general problem is this problem of what I call delegated learning and testing. So in delegated learning and testing, like, let me give you an example. So a very concrete example is consider the task of purity testing. So in purity testing, you're given an unknown n-qubit state row, and you're promised it's either maximally mixed, like it's the identity over the dimension, or it's just like a randomly drawn pure state. So these two things couldn't be more different. Like either it's a pure state or it's maximally mixed, and all you have to do is decide which is which. This is called a property testing problem. Okay, and so now imagine you have like Alice. Now she has a quantum computer, but it only has n qubits of memory. And you have Bob, and he has 2 n qubits of memory. So now Bob has this like resource of space. And again, like, so what people have done in the last like years is that they've proven that you really need quantum memory to do this. If you're Bob and you have 2 n qubits of memory, you only need a constant number of copies of the unknown state. But if you're Alice and you have like only enough memories to just store the state, and then you have to measure it before you can get another one, then you need exponentially many copies. But then the question is natural. What happens if if Alice asks Bob to use his big quantum computer to solve the problem for her? And it's the exact same thing. Like Alice has n qubits, Bob has like many. They both have access to the state. Alice knows that she would need exponentially many if she tried to do this herself. So she pays Bob to like help her do it. And importantly, if Alice trusts Bob, then she doesn't have to do anything. Because she said to Bob, please just tell me whether the state is pure or not. And Bob says it's pure or it's random. But when she doesn't trust him, like she has to do something. They really have to interact in like a meaningful way. And So like, what if Alice doesn't trust Bob? And in particular, is there some protocol which lets her use less than exponentially many queries and still be guaranteed that she gets the right answer? She should either get the right answer or she should know that Bob is cheating and fine him, basically. Okay. Another example is basically the same. You consider purity testing, but now you imagine the setup where Alice has what's called a statistical query oracle and Bob has what's called a standard copy oracle. So this is jargon, which means that Bob can do like full state tomography. Like Bob's allowed to like learn everything he wants about the state, but all Alice is allowed to do is make measurements of like specific observables and get like expectation values out. And again, it turns out Alice needs exponentially many queries, Bob needs constant number. And you can ask the same question. If Alice doesn't trust Bob, is there an interactive protocol which lets her do better? And so the general picture is this. Let's consider any learning or testing problem for which there's something that we can call a relevant resource. And the resource could be memory. It could be the oracle type. It could be the quality of the gates. And basically you consider Alice doesn't have the resource. Bob has the resource. Alice has some lower bound. She needs to use at least some number of queries. Bob knows he can do it with his resource. So he wants to, like, what happens if we let Alice interact with untrustworthy Bob? Like, can we develop interactive protocols for the verification of learning and testing that we've delegated to an untrusted third party? So Alice is resource constrained, Bob is resource unconstrained, but he's not trustworthy. And can we develop protocols which lets Alice like beat her lower bound? Okay, and there's a long list of examples. So like, for quantum memory as a resource, all of these problems, quantum state tomography, Pauli shadow tomography, purity testing, unitarity testing, symmetry classification, learning polytime quantum processes, we know that you need quantum memory to do these efficiently. If you have an oracle as a resource, there's a whole other list of problems that you can't do if you have a weak oracle, and you can do if you have a strong oracle. And then, of course, we know that noiseless gates are a resource. If someone has a noiseless quantum computer and someone has a noisy one, of course, there's things you can do with the noisy one and non-noisy one. Okay, and so here's the final slide. Nice, it's like just on time. These are the results. The first thing is bad news. And what we can prove is that for a wide variety of settings, so like I've shown you, there's really like a lot of problems that fit within this framework. We can show that Alice just like can't do anything. There's no way that she can interact with Bob and be sure that she's going to either get the right thing or detect the cheating, unless she basically uses as many resources as she would need to use herself to solve the problem anyway. Basically, like if you can, like this is in a wide variety of settings. And basically, this is whenever Alice has less memory than Bob, and when they can only communicate via classical communication. So this is kind of bad because this is the world we live in at the moment. Like we're memory constrained, and we can only communicate with IBM and Google and Amazon via classical communication. So for like all of those problems that I listed there, like we proved that like you will never come up with a verification scheme, like they don't exist. But the good news is that these limitations can be avoided if you're allowed to like exchange quantum information. So one day we will hopefully have a quantum internet, and when this quantum internet is around, like I can give you a specific interactive proof protocol. Okay, and then we can improve these in like different technical ways, which I'm not so interested in telling you about. And yeah, you can find these results in this paper, Interactive Proofs for Verifying Quantum Learning and Testing. And so yeah, with that, thank you. And like all of this work was done with like many very nice collaborators over the years. And it's also like super important for me to say thank you to all of them for working on these things with me over the years. So yeah, that's what I wanted to tell you, and of course, I'm happy to answer any questions. Yeah.
Yeah, thank you very much. Question asked in there so that the people online can listen as well. Any questions?
What about kernel methods?
What about quantum kernel methods? Yeah, it's a good question. Like, I'm busy writing a paper about dequantization of quantum kernel methods. And I would say the jury is out. Like, basically, the situation for quantum kernel methods like is essentially the same as the situation for supervised learning, in the sense that like we now have like a pretty good picture of the conditions under which. So basically, for kernel methods, we've like been in the process of doing exactly the same thing as we did for supervised learning. First, we tried to characterize the set of classical kernels, which contains the set of quantum kernels. And this is like a new class of kernel that we call entangled tensor kernels. And then we like try understand the properties of the circuit that you need in order to be able to guarantee that if you use a specific entangled tensor kernel, you will be guaranteed to beat like what happens if you use the quantum kernel. But it's definitely not conclusive in the sense that, yeah, like it makes some small progress in ruling out some set of quantum kernels, but I would say the jury is pretty much largely out. The only thing I would say is that like my personal opinion about quantum kernels is a little bit of like a tiny bit of like who cares, in the sense of that like quantum kernels, I mean like kernel methods are just like far from the state of the art in machine learning. Like I really think that even if we can't prove something about quantum kernel methods one way or another, I like my personal perception is just like hard to imagine how these will be like competitive with like state of the art classical methods. For generic problems, I think there might be like very specific structured problems where like kernel methods just happen to be the right thing, but like that's the kind of work I would do in quantum kernel methods, like understanding really what structures are like important ones. Yeah.
Is there proof that a quantum kernel is actually better, faster?
So like basically like I showed you this game that we played for generative modeling, where we said like, let's construct like a very specific problem and a very specific algorithm. And for this very specific problem, we can prove that this very specific algorithm definitely does better than classical algorithms. So like people did the exact same thing for quantum kernel methods. They showed that there's like a very specific problem. It's like you use the discrete logarithm to define the problem exactly like we did. And then you show that there's like a kernel, a quantum kernel that you can design that implements the discrete logarithm and then can solve the problem. But like, you can't do it classically. So basically like there's that proof, but that proof is like exactly as useful as the proof that I presented to you. Like it's a necessary but not sufficient condition. Like you have to do it if you want to go past it, but like once you've done it, you haven't actually like provided any evidence for anything. Yeah. Yeah.
Any questions from
the people?
Sorry, I would ask the people online because I can't say.
Like the idea of the market situation where a quantum computer needs less data, there will be less data.
Yeah.
I mean, just naively, like kind of intuitively, that seems strange to me that would be possible, because presumably there's a certain amount of information in the data, and like there's like noise and issues in the data. So there's like no ground truth of like what is a cat versus a dog. You just need to see. Like, can you just maybe say a bit more about that?
Yeah, so I mean, there is this field called query complexity. I mean, like, the way I think about this is like there's a magic box, and every time you push a button, like out comes an example. And so the question of how much data you need is like how many times you have to push that button. And like interestingly enough, there are like very good proof techniques for lower bounding query complexity. So you can actually prove like sometimes you can prove that for different types of algorithms, they do need different types of data. So as unintuitive as it is, like, and I can send you some examples of problems where like this type of algorithm needs at least this much data, but this type of algorithm can do with less. So that's the first answer. And then the second type of answer is like there's different types of data. And like what people in quantum learning theory like to do is consider like what they call quantum data, which is basically like quantum states that encode like the function in the amplitudes, for example. And so like you can also study like different types of data, and you can show that, well, a classical computer can't use quantum data, it's like impossible. But you could show that, okay, like a classical computer needs at least this much data, and a quantum computer, if it had access to this like exotic type of data, and like who knows where it got it, or if you ever can make it, but like if it did, like it could do better. Like that's kind of like the easiest way out, and that's what like we do and other people do, but it's also a bit ridiculous in the sense that like that data is not floating around anywhere. We don't really know how to make it. Yeah.
Not yet.
Not yet. Okay.
Yeah.
Any other questions? Other questions from the online audience? Sorry, no. Doesn't see
people on.
Yeah. Okay, but keeping a low profile. Okay, man. Last question. Yeah.
You mentioned something about looking at the relative cryptography and
Yeah. Like so, like I think about cryptography and ML as like inverse fields, in the sense that what is the like prime task of cryptography? Like, I want to send you something, okay? And now we want to like come up with a scheme where like I send you something, and there's Eve. She's like eavesdropping on us, and we just have to assume that everything I send you, she makes a copy of. okay, and you've designed a good cryptography scheme. If like you design something that has the property that you can prove that no matter how much data Eve gets, no matter like how many times she eavesdrops on us, she can't learn what I'm sending you. Like the whole of cryptography is based on proving that certain learning problems are hard. Like cryptography always defines a learning problem. Like and so like cryptographers, they try to prove that learning problems are hard, and then like machine learning people are doing the exact opposite. They're trying to like come up with like algorithms that work to extract data. So like you can think of like these two people as being on like different teams, but like if you're a machine learning person like I am, that is very interested in lower bounds. Like I'm very, very interested in knowing that I'm not so interested or good in coming up with algorithms that work. Like I'm interested in good and good, I think, at like proving that algorithms can't work. And like to do that, like cryptography is just your best friend because they know how to prove that algorithms can't work. Like they have to do that all the time to convince you that their cryptographic schemes are safe. Yeah.
That's cool. And are there like anything where people like explicitly use ML to decrypt?
Yeah. Like this is a big thing in like modern cryptography. Like people use machine learning algorithms to attack like cryptographic schemes. There are these things called physically unclonable functions, and like this guy Jean-Pierre Seifert kind of invented them, and like then he kind of did a total turnaround and like started attacking them with machine learning algorithms, and like turns out he broke them. And
was he able to?
Yeah, I mean he had a very
This is why the developed the adversary machine learning algorithm, well, the adversary, because they I know that lots of cryptographic companies do that. They actually employ machine learning to learn the attacks of machine learning on their,
interesting, crazy.
yeah. So should they, yeah.
Right. So this guy is
machine
like,
learning to beat the machine learning.
yeah. This guy had a very interesting job. Like, okay, now he's a professor at the Technical University of Berlin, but before that he was at Siemens, and like I think for like 15 years, his job was basically to break. Like they were just like, please try your best to break like every cryptography protocol we have, and he was like amazingly successful at it. And like I don't know like which ones he broke and which ones he didn't, but like he broke a lot of them. And like you do them using relatively naive methods often because
Yeah, I mean, a follow-up question would have been like, are those type of ML models also like deep network kind of things, or is it more tailored things with like the kind of problem?
honestly, like I'm kind of a little bit outside of my expertise now in the sense that I couldn't tell you. But like there's a good lesson here, which is that like lower bounds are conditional. Like there is no, so like all of the lower bounds that I've spoken about are lower bounds of the type, like under this assumption, like no one can break it. And like then the name of the game for people on the other team is just be like, okay, can I design algorithms that don't have that assumption, right? And like there are some unconditional lower bounds in query complexity, because you can just say that like, well, if you don't see this many examples, there's just not enough information. But when it comes to time complexity, like there's not a single unconditional lower bound. Essentially, every lower bound at the end reduces to like, this is safe unless P equals NP. But if P equals NP, then like everything breaks.
Okay, if there are no more urgent questions, Ryan, thank you very much for coming. And now that you're close by, I hope we will see you way more often than the last couple of years. Yeah.
Yeah, I should have put my email address on here. Like
Yeah, we can email
so
sort it out.
I just reiterate that, like, so I'm now like 45 minutes away down the road. If people have questions, if you have ideas, if you're interested in learning like a bit more about any of these topics, like they're all active, they all have like many open threads, and I'm happy to talk, and you can email me and like we can figure something out.
Excellent. So thank you very much again. Thank you.